When most people think of teleportation, they think of, gotta go! Yes, I got it. Well, they think of teleportation of objects like you and me. Quantum teleportation is different. It's the teleportation of quantum information.
Let's go through an example to better explain this. A quantum state is a property of a particle. If our particle is an animal, then its state or property could be the species of that animal. For this example, the state of our animal is going to be a cow with horns and spots. To transfer the cow's properties and information through quantum teleportation to a location very, very far away, that original cow will have to be destroyed to measure its properties, and those measured properties of the cow are sent to a new location. Then, in that new location, these properties are used as a blueprint to construct a new cow with the same attributes of horns and spots. The transported cow isn't the same cow. It just has the same properties. Now let's learn a little bit about the math behind this phenomenon.
To learn more about quantum teleportation, we need to learn more about gates. Not those gates, computer gates.
In a classical computer, there are two states, on and off. When an electrical current is run through a gate, it manipulates what happens to the state. Not gates are like your annoying sibling. When you turn the lights on, aka create an electrical flow, they turn it off. In a quantum computer, these quantum bits, or qubits for short, are in superposition, which is a state where the bit is both on and off with a probability of each state occurring. The quantum equivalent of the NOT gate is when the annoying sibling switches the probabilities of each state occurring. Control polygates depend on the first qubit whether the second qubit will have its probabilities changed. So if the first qubit is on, then the second qubit's probabilities will get changed. If the first qubit is off, then the second qubit's probabilities will not be changed. Hadamard gates entangle two qubits. So if you know the probability of one qubit, you'll know the probability of another qubit. Gloves can simulate quantum entanglement. So let's say this is a right glove on state and this is a left glove off state. If we mix them up and measure one of them, since this is a left glove off state, then we know this one's going to be a right glove on state. To conduct quantum teleportation, there needs to be at least 3 qubits, 2 belonging to, say, Alice and 1 to Bob. When these qubits are put through a series of controlled NOT and Hadamard gates, Alice is able to measure her 2 qubits and send the classical information to Bob. From the information Alice sends to Bob, Bob is able to replicate Alice's qubit. This amazing science isn't just theoretical. Quantum teleportation has been implemented over 14,000 kilometers away. Thank you!